Let's examine the phenomenon called stall more closely. We've said that the angle of attack of a compressor blade is the result of the axial velocity of the air passing across it and the rotational speed of the blade. We said that the forces of the air's axial velocity and the engine RPM combine to form a vector, which allows us to find the actual angle of attack of the airflow over the blade. So, a compressor stall can be caused by an imbalance between the rotational speed of the blade and the axial velocity of the air passing across it, which can occur for various reasons, some of which we'll now examine. Use the buttons to increase or decrease the engine RPM and see the effect that has on the blade angle of attack. Excessive fuel flow, which may be caused by abrupt throttle opening during an attempt to gain rapid engine acceleration. The back pressure generated in the combustion chamber may rise to the extent that it will cause a reduction in the axial velocity of the air passing through the compressor. Engine operation either above or below the engine design RPM parameters. Engine overspeed or underspeed will increase or decrease the rotational speed of the compressor blades. Situations which may either increase or decrease the angle of attack to the point where the efficiency of the blade is destroyed, and thus the axial velocity of the airflow is reduced. Turbulent or disrupted airflow to the engine intake. This will reduce the axial velocity of the airflow through the whole of the compressor. Contaminated or damaged compressor components, rotor blades or stator vanes, which will reduce the efficiency of the compressor as a whole. This will cause an increase in the axial velocity of the airflow through the compressor because of the decreased compression ratio. A contaminated or damaged turbine will not be capable of generating the power required to drive the compressor at the correct speed. This will make the compressor incapable of generating a sufficiently high compression ratio, which in turn will mean that the axial velocity through the compressor will increase. Excessively lean fuel-air mixture, which could be caused by abrupt throttle retardation. This will cause the axial velocity of the airflow through the compressor to be increased by the decreasing combustion chamber back pressure. Any of the conditions just mentioned can cause a compressor stall to commence, and as soon as it does, there is a partial breakdown of airflow through the engine. The indications of compressor stall can be any or all of the following. Fluctuations in the engine RPM. An increase in the vibration level of the engine, which can generate noise, which may become audible in the cockpit, depending on whether the engines are wing-mounted or rear fuselage-mounted. And an increase in the exhaust gas temperature, otherwise known as EGT. This latter effect, the increase in exhaust gas temperature, is caused by the fact that there is less air going to the combustion chambers. Hence, there is less air to cool the products of combustion, the exhaust gases. Remember that compressor stall is a progressive phenomenon. It could, in theory, initially occur at just one blade, subsequently worsening to encompass the whole of one stage, and then, if nothing is done to prevent it, it can affect the whole engine. The progressive deterioration of the speed of the airflow through the engine, caused by the stall phenomenon, will eventually cause a complete breakdown of airflow through the engine, which we said was called a surge. In severe cases, a surge could cause an instantaneous reversal of the airflow through the engine, with air being expelled through the engine intake with a loud bang. If surge does occur, the throttle of the affected engine must be closed slowly, and the cause investigated. Surge is most commonly caused by either fuel system malfunction or engine control mishandling. In extreme cases, a surge can inflict such large bending stresses on the compressor rotor blades that they contact the stator blades, with potentially catastrophic results. Apart from the loud noise that usually accompanies a surge, there is a large rise in the EGT, and the resulting loss of thrust may cause the aircraft to yaw. The pilot must always be conscious of the causes of stall or surge if he is to prevent either from occurring. Smooth operation of the throttles, both when advancing and retarding them, will ensure reliable and prompt response from the engine. The pilot must also be very aware of the restrictions which RPM and the ambient density place upon the power plant, and amend engine handling accordingly. Operation of the engine outside the optimum RPM and axial velocity range is inevitable. Although design criteria are, after all, aimed at producing the greatest engine efficiency near maximum RPM, engine operation at power settings below that point has to occur if we are to be able to throttle the engine back from full power. So, engine operation below the maximum power level means that we are committed to altering the rotational speed of the compressor, and also the axial velocity of the air as it passes through the engine. Unfortunately, by doing either of these, we are encouraging the onset of stall and surge. Systems that ensure that surge and stall do not happen have to be fitted to the engine. Here are some of those systems. Variable Inlet Guide Vanes, or VIGVs. Variable Stator Vanes. Compressor bleeds. Multi-spool compressors. Variable Inlet Guide Vanes, or VIGVs, are fitted to engines which have a particular problem with inherent compressor stall at low RPM or during engine acceleration or deceleration. Variable Inlet Guide Vanes are fitted just in front of the first rotor stage. Variable Inlet Guide Vanes can be automatically pivoted around their own axis to vary the path of the airflow going into the compressor, so maintaining the proper relationship between the compressor rotational speed and the velocity of the airflow through the front compressor stages. At low compressor speeds, the variable inlet guide vanes are angled to impart the greatest amount of swirl to the air, thereby correcting the relative airflow to obtain the optimum angle of attack over the rotor blades. Maintaining this optimum angle of attack allows a smooth and rapid engine acceleration. At high compressor speeds, the variable inlet guide vanes reduce the swirl imparted to the airflow, thereby maintaining the correct angle of attack of the air flowing over the rotor blades. After the first rotor stage has been successfully negotiated, the airflow may still have problems further down the compressor, when the engine is operating at other than its optimum conditions. To minimize those problems, some engines are fitted with variable stator vanes. Variable stator vanes can be pivoted automatically so that as the compressor speed is reduced from the optimum design value, they are progressively closed to maintain the airflow onto the following rotor blades at an acceptable angle of attack. In some engines at low compressor RPM, the relationship between RPM and airflow axial velocity may not be maintained to give the rotor blades the optimum angle of attack, unless some of the excess volume of air is allowed to escape from the intermediate stages of the compressor. If a compressor bleed valve, like the one shown here, is fitted to the compressor casing at a position adjacent to the intermediate stages of the compressor, it can be opened at low RPM and during engine acceleration to allow some of the excess volume of air to escape. This will have the effect of bringing the axial velocity of the air in the earlier stages of the compressor closer to the optimum value, and also of reducing the choking effect in the rear of the compressor. This diagram shows a pneumatically operated compressor bleed fitted to the intermediate compressor section of a bypass engine. When the engine is operating at reasonably high power settings, the high pressure or HP compressor output will be high enough to lift the diaphragm in the actuator valve. allowing high-pressure air to maintain the bleed valve closed. Conversely, when engine RPM drops, the high-pressure compressor output pressure also drops. Eventually, the drop in pressure will allow the actuator valve diaphragm to fall, and its attached valve to close off the supply of HP air to the bleed valve. Consequently, with its supply of HP air cut off, the bleed valve opens, allowing a reduction in the volume of air through the compressor, which would otherwise tend to choke the flow of air through the engine. This combination of optimum airflow velocity and reduced choking will ensure that compressor stall is less likely to occur during the time the bleeds are open, but there are disadvantages to the use of the system. Opening any compressor bleed, whether it's a bleed used as a stall preventative measure or alternatively a bleed used to supply air for aircraft services, decreases the mass airflow through the engine. A decrease in mass airflow through the engine will cause a drop in thrust for a given throttle position, which raises the engine's specific fuel consumption, or SFC. A decrease in mass airflow also raises the engine's exhaust gas temperature, because the amount of cooling air available in the combustion chambers will have decreased. The design of early axial flow engines was developed by adding more compressor stages on one shaft to obtain higher and higher compression ratios. Unfortunately, having many compressor stages on one shaft makes it increasingly difficult to retain the engine's operational flexibility in terms of being able to operate it over a reasonable RPM range. Compressor blade angles are arranged to give peak engine performance around maximum RPM, when the values of the axial velocity of the airflow and the rotational speed of the blade combine to produce a vector which is the optimum angle of attack of the airflow over the blade. Any reduction of engine RPM changes the symmetry of the vector diagram relating the RPM to the axial velocity. Thus, the angle of attack no longer retains its optimum value. Because of this, compressor stall becomes an ever-present problem at lower engine speeds. So, to overcome the tendency that early axial flow engines had of the compressor stalling at low RPM, designers split the compressor, initially into two separate sections. The two sections were called respectively the high-pressure or HP compressor and the low-pressure or LP compressor. Subsequently, in later, more powerful engines, designers split the compressor into three sections by adding an intermediate pressure or IP compressor. Each compressor section is driven through a shaft by its own turbine. At any given power setting, the speed of rotation of the compressors increases in proportion to its pressure status. Thus, the intermediate pressure compressor rotates faster than the low pressure compressor, and the high pressure compressor rotates faster than the intermediate pressure compressor. We said earlier that together the compressor, the turbine, and the shaft upon which they are both mounted form a spool. By designing the engine so that, upon closing the throttle, the speed of the low-pressure spool falls off more rapidly than the intermediate pressure and high-pressure spools, it can be arranged that the optimum shape of the vector diagram relating to compressor blade angle of attack can be maintained over a much greater engine RPM range, thus greatly reducing the chance of compressor stall. When referring to the speed of rotation of the spools, it's usual to call the speed of rotation of the low-pressure spool N1, and the speed of rotation of the next spool in the engine N2. If the engine has 3 spools, then the speed of rotation of what would be the high-pressure spool would be called N3.